Okay, so this person is spear fishing, but every time he throws the spear at the fish, he keeps missing. Why is that? Well, he thinks the fish is here, but in reality, the fish is actually here. This is because of an effect called refraction. Refraction is a change in direction of a wave when it travels from one medium to another medium. And this is caused by the change in speed. So actually, light is faster in air than it is in water. And so when it changes medium, it's also happening to change direction in this case. To understand this, let's look at a car. It's going from smooth road to a muddy track. It's coming along like this. And you see that wheel that's hitting the mud first? Well, that's going to get stuck a bit and it's going to slow down, while the wheel that's still on the smooth road is going to keep going. And that's going to cause a car to change direction. And it's going to go like this. Okay, so what's happened? So if we draw this dotted line, that's called the normal, and that's 90 degrees to the boundary, in this case between the muddy road and the smooth road. And we can see the angle, it's getting smaller. The angle between the normal and the incoming car and the outgoing car, it's getting smaller. So we say that the wave has bent towards the normal as it slows down. Whenever it slows down, it bends towards normal. Actually, when it speeds up, it's going to bend away from the normal. Okay, so here's some examples. So we've got the light ray that's coming in from air into glass, and this angle is what we call the angle of incidence, and this one is what we call the angle of refraction. And as you can see, when it goes from air to glass, it slows down, so it bends towards normal. But in this case, you can see the angle of incidence when it comes from glass to air, it's actually bending away. So the angle of refraction is larger. Okay, so as example, so if this was 50 degrees, this would be 30. If there's 20 degrees over here, then it increased to 45 degrees. To remember this, we can use a mnemonic, fast. So if it gets faster, it bends away from the normal. So FA, faster, away. And if it gets slower, it bends towards the normal. Let's look at what's going on in a bit more detail. Let's say the light is coming in like this. We can represent the wave using a wavefront like this. So it's coming head on in this example. And so the wavefront is, think of it as like if you look at waves at the beach, you can see all the peaks joined in a line like this. So the wavefront is moving towards the water, and then it enters the water, and then when it does so, you can see they get kind of squashed together. They're closer together like that. So what's happened is the speed has actually decreased, but also the wavelength has decreased. And you could tell because the distance between the lines, the wavefronts, is the wavelength, which is represented by the Greek letter lambda here. Okay, let's look at what happens when it goes from water to air. So we've got the wave coming in. Again, I'm representing the wavefronts, and the distance between them is the wavelength. And as you can see, when it goes into air, it speeds up and they get further apart. So speed has increased and the wavelength has also increased. Now, the thing that doesn't change is the frequency. It's constant in both scenarios. So in that scenario, the direction didn't change because it was coming head on. But in this scenario, let's look at the wavefronts coming in. See the part of the wavefront that hits the medium, the water first, is going to slow down. So you can see it's bending towards the normal like this. And then it keeps going. And also the wavelength has decreased as well. And the direction has changed, bent towards normal. Okay, so that's why we always say waves that go into more dense medium but slows down, bend towards normal. Let's look at what happens when it's going into a medium where it's faster, so from water to air. It could also be from glass to air as well. So you can see the wave coming in. The part that hits the air first is going to speed up and it's going to bend away. Okay, so it's bending away from the normal like this. Example number one, here we've got light going from air to oil, and we have to complete the diagram to show the wavefronts and the ray. So when it goes into oil, it's going to slow down. It's more dense, so it's probably going to slow down. So I'm going to have it bending towards normal. And also look at how it made the wavelength smaller by making the wavefronts closer to each other. Okay, so it's bending towards normal like this. So we can confirm that slower means towards normal. And you can see the the wavelength has decreased as well. Example 2. The diagram shows light traveling from glass to air. Explain why the wave doesn't change direction. So we can see from the diagram that it is speeding up. Okay, the wavelength is increasing as it goes into air because it's less dense. However, the direction isn't changing. This is because the light ray, is coming along the normal. So we say the angle of incidence is 0, or we can say the light ray is traveling along the normal. Okay, so that means every part of the wavefront is going to slow down at the same time, unlike when it comes in at an angle where one part slows down before another. Part B, explain how the wave changes as it enters a new medium. And here we've got water and then it's going into an unknown medium. Well, we can see the wavelength, the waves are further apart. So the wavelength is increasing. And we can show them using this, the distance between the wavefronts. And that means the speed is probably increasing as well. What doesn't change is the frequency. The frequency remains unchanged.